efficient and methanol-resistant electrocatalysts for the oxygen reduction reaction based on bidentate phosphine-carbonyl clusters of rhodium. Fuel cells are an emerging technology for clean energy production. When they use hydrogen as fuel, they are capable of producing electricity and heat with water as the only product. Some organic compounds, such as methanol, can also be used as an indirect source of hydrogen, and hence, as fuels. In this case, an organic subproduct or carbon dioxide is also obtained. Fuel cells consist of an anode, where the fuel is oxidized to release electrons and protons, and a cathode, where the protons and electrons react with oxygen to produce water. The protons cross to the cathode through a polymeric membrane, while the electrons travel through an external circuit, where they can be exploited as electric energy. The cathodic reaction, the oxygen reduction reaction, has the slowest kinetics of the two, and the development of electrocatalysts to increase this reaction's kinetics is an important area of research. Synthesis of the catalysts. 3 clusters of rhodium with carbonyl and bidentate phosphine ligands were synthesized in refluxing orthodichlorobenzene by the reaction of hexadecarbonyl-XR-rhodium with methylenebisdiphenylphosphine, orthophenylebisdiphenylphosphine or ferrosnodylbisdiphenylphosphine. The structural characterization of these compounds was performed by means of Fourier transform infrared spectroscopy, energy dispersive X-ray spectroscopy, scanning electron microscopy, X-ray diffraction. Fourier transform infrared spectroscopy spectra show that the functional groups of both carbonyl and phosphine ligands are present in the molecular structure of the catalysts. The mass % elemental chemical composition determination by energy dispersive X-ray spectroscopy revealed the presence of chlorine atoms, which suggests the presence of orthodichlorobenzene molecules in the molecular structure of the catalysts. Scanning electron microscopy images exhibit an irregular superficial structure that can contribute to increase the surface area of the electrocatalysts, which is an advantageous property for these materials. X-ray diffraction patterns show an amorphous structure. The absence of the characteristic peaks for metallic rhodium around 40 degrees and 47 degrees indicates that the catalytic activity of these clusters can be attributed to their molecular structure, and not to residual metallic rhodium. The electrochemical characterization was carried by a rotating disc electrode technique in an acid medium, in the absence and presence of methanol. These new clusters exhibited an important activity towards the oxygen reduction reaction even in the presence of 2 molar methanol, which makes them potential catalysts as cathodes, not only in hydrogen polymer electrolyte membrane fuel cells, but also in direct methanol fuel cells. The kinetic parameters of these clusters are similar to those of platinum, with the advantage of their resistance to methanol. This contaminant drastically reduces the activity towards the oxygen reduction reaction of platinum. The best performance was achieved by the cluster with methylenebisdiphenylphosphine ligands.